Good morning, ladies and gentlemen. The next part of our magnetism unit covers electromagnetism, which was first discovered by Hans Ørsted in 1820 when he was doing a demonstration in front of his classroom that as a physics teacher himself, he was trying to show off this newly discovered electricity and how it could power a light bulb. But he happened to have a compass on the desk next to him as he was doing this experiment, and he noticed something peculiar whenever he turned on the light bulb for his class.
Magnetic fields is with a compass. I've got a wire. I'm going to put electricity through that wire, and I've got it surrounded by compasses. Compass points towards a magnetic field. And if you were to bring a strong magnet near it, they would point towards it. So I got a little strong magnet in my hand. You can see they point towards it. And an interesting phenomenon takes place. I'll get it lined up. When we put electricity through a wire, it creates a magnetic field. And the magnetic field is just going around that wire.
Hans Ørsted actually noticed that the compass was actually moving every time he turned on the current. And as you can see in this diagram over here, there's a magnetic field that's going through the, going around the wire itself. But the magnetic field can change based on the direction of the current itself. So whether going clockwise or counterclockwise depends on the direction of the current. So to characterize this phenomenon and to better teach it, scientists came up with what they call the right-hand rule. So basically, the thumb is equal to the current, and your fingers is equal to the magnetic field itself. So the current happens to be going up this wire, your thumb would point up, and your fingers would wrap around. And your fingers show which way the magnetic field is going. The current's going the opposite direction, then the magnetic field goes in the opposite direction as well. Okay, so you can see over here how the magnetic field is represented by the fingertips themselves. So if we take a quick look up here, for example, again, so that means that around this wire, when there's current going up, there was a magnetic field going around, and the compass happened to show which way that magnetic field pointed at the same time. So as we look at our diagram over here, remember the thumb is equal to current. The curl fingertips is equal to the magnetic field, which represented with the letter B. So in each case, if you were to use the hand rule, just hold up your pen and practice wrapping your fingers around it, you can see exactly how the magnetic field would look. But the thing is, it's kind of hard to draw a three-dimensional representation on a flat piece of paper. So scientists came up with an alternate way of explaining what's going on using dots and X's. A dot simply means out of the page, and X means into the page. And the best way to remember that is to remember that on a treasure map, X marks the spot, and you always dig in wherever X is. So in this case over here, when I put my fingertips around the wire again, in this case, it will be going into the page on the right-hand side of the wire, and it will be coming back out of the page on the opposite side. So you can, if you can imagine, it goes in and then comes back out, goes in and comes back out in this example. If the current was to go in the opposite direction, then your thumb will point down and your fingertips wrap in the opposite direction as well. And we would represent it like this. But of course, it's annoying to draw like that. So with our thumb pointing down, our fingertips go into our paper on the left-hand side, and they come back out on the right-hand side. So there's a constant magnetic field being generated at huge distances around every current-carrying wire. When you're dealing with a loop, however, it's still exactly the same rule. But with a loop, you have to realize that your current will travel around the loop. And notice how my fingertips are always going to be inside in this case. So over here on the left-hand side of the loop, with my thumb pointing up, I should note that the magnetic field is going into the page on one side and out of the page on the other side, while on the opposite side, even though current is going down, it's still holding true that the magnetic field is going into the page, inside the loop, and out of the page, outside the loop. And it doesn't matter whether the loop's tilted or it's straight. The fact is that when your hand is following the loop all the way around, your fingers are always pointing in the same direction inside the loop. So inside the loop, the direction of the magnetic field is the same from any point. Okay? So in this case, as demonstrated over here, the magnetic field is pointing up. According to our loop rule, it goes, in this case, it's going into the page on one side, out of the page on the other side, but it's going to be out of the page at every single point. And over here, we just have another representation of what the dot versus X diagram will look like for any loop. Now, understand, of course, that this right-hand rule is based on conventional current, which Benjamin Franklin came up with. If we had to deal with electron current instead, how would this really change? Because electron current, as we know, flows in the opposite direction of conventional current. With conventional current, if we were to use our hand rule, thumb points to the right, the fingertips go into the page underneath and out of the page above. So we end up with X's underneath and dots above. If with electron current, because it's a negative charge, anytime it's a negative charge, we're going to use our left hand instead. So with our left hand now, pointing the electron current to the left, we can see that it goes into the page underneath, out of the page above. In other words, it's the exact same answer. So which is why nowadays we still don't mind using conventional currents, because as long as we use the right-hand rule, we'll always understand which way the magnetic field is going. Whether you use the right-hand rule for positive charges or the left hand for negative charges, it still ends up being the same result. Okay. You guys are also going to have to be able to identify the direction of the current simply by looking at the direction of the magnetic field. And if you take a look at the top left example over here, you can see with the loop, it's going into the page on the outside. So if I actually took my right hand and stuck it into the page on the outside, and you can see that it comes out of the page on the inside, I can see that the current is going up on the right-hand side and is going down on the other side. So overall, I have a counterclockwise current. With the second example, we can see that the fingertips go into the page underneath the wire. So as it goes underneath the wire and it wraps around, my thumb is pointing to the right. So overall, this current is going to the right. Okay. And of course, understand that because a wire is generating a magnetic field, it literally becomes a magnet itself also. So if you were to put two magnetic field generating wires next to each other, two current carrying wires next to each other, they should attract or repel. So if I use my right hand, and I draw what the magnetic field looks like around each wire, I can see that it's going into the page on the right, out of the page on the left. And the same would be true for the right wire. If we were just to assume that dots were north and X's were south, we can see that Well, if you have opposite poles next to each other, wires that have current going in the same direction are actually going to attract towards each other with a force that we will be able to calculate later on. If you have wires carrying current in the opposite direction, however, south and south, in this case, because they are the same pole, they would actually repel away from each other. And this demonstration by MIT shows it very well. And you can see, in this case, whether the wires are attracting or repelling. He's simply changing the direction of the current within the wires, and based on when their current is going the same direction, they are going to attract, and when they go in opposite directions, they are going to repel. Okay. And if we talk a little bit more about loops, we've already mentioned that loops always have the magnetic field going in the same direction inside, which means that if you were to use the hand rule over here, you would note that it's going out of the page, inside and out, and into the page on the outside. This is using my right hand rule. The fact is, that's just one loop of wire. If you take multiple loops of wire and wrap it around and around and around and around, you're creating what we call a solenoid, or a coil of wires. And each loop of wire is going to generate its own magnetic field inside. So ultimately, you have a magnetic field that's very strong being generated within the coil of wires. And if we were to use our hand rule for one of these loops, we can see that north would be on one side, south would be on the other side. Basically, as the current is going up the coil, okay, the fact is that it creates a magnetic field inside the loop on one side, and you end up with the magnetic north on the left and magnetic south on the right. This can be clearly modeled. In this case over here, we just have a coil of wire embedded, and with the iron filings, we can see the magnetic field lines going straight through, with north on one side and south on the other. In fact, it's basically as if it's a giant bar magnet itself. And because it's a giant bar magnet itself, you would have magnetic field lines going out of north and back into south afterwards on the outside. And we can see that over here as well. Now, if you want to make it even stronger, you take that coil of wires and wrap it around either something that's made out of iron, cobalt, or nickel, because those are three metals that happen to have very easily influenced magnetic domains. So in this case over here, you would generate a magnetic field within the wires, within the coil of wires, which creates a magnetic field within the iron, which means that you end up with north on one side and south on the other. Which is why when you wrap a wire around wire and connect it to a battery, it ends up being magnetized and you can pick up different things. If we were to do a couple practice questions here, what is the direction of the magnetic field at point P? In this case, they're clearly labeling for us that's an electron current, which means I use my left hand. Okay? With my left hand now, I'm going to simply look at above and point my thumb to the right. I wrap my fingers around the wire, and when I wrap my fingers around the wire, I note that's going into the page above the wire and out of the page below the wire, which means that at point P, the magnetic field is out of the page, because every point inside the loop is going to be exactly the same direction. Over here, they show us the magnetic field, and they're asking us what is the direction of current. Now, if it's not stated, we're going to assume it's conventional current. In this case, so I will use my right hand, and I will note that going into the page on the right-hand side and out of the page on the left-hand side, which means if I use my hand and it wraps around, okay, it means that current is going up the wire.